There are times, there are times in calculus when in order to solve for the integral, you're going to have to use long division. One thing that can help you see that you need to do that is by looking at the powers. When the biggest power in the numerator and the denominator are equal, like in the example you see here, or if the biggest power in the numerator is bigger than anything in the denominator, that's a sign you probably need to consider long division. So here we go. We need to use long division because we see the power on top, x squared, or the biggest power on top, x squared, is the same as the biggest power on the bottom, also x squared. So we need to use long division to be able to solve this. So when you do long division, remember, you do the steps, same steps you did with dividing numbers, which is divide, multiply, subtract, bring down. So we'll start by dividing. We do x squared divided by x squared, which gives us 1. Then we multiply 1 times x squared plus 1. So 1 times x squared and 1 times 1. Notice I did put the 1 over there with the other constant because I want to keep the like terms together. Now I need to subtract. I've divided and I multiplied. Now I subtract. X squared minus x squared is 0. X minus no x is x. 1 minus 1 is 0. So I'm just left with x. And I can't divide any further because x squared won't go into x, it's too big. So x is our remainder. And remainders, when you divide, always go over top of whatever you're dividing by. So it turns out this fraction right here is equal to 1 plus x over x squared plus 1. Now I'm still in an integral, but I've now changed the form of the integral to be this. And this we can handle using U-Substitution. If it helps you, we can think of this as two separate integrals. Just split up the 1 and the x over x squared plus 1. So just to save myself some room, I'm going to move this down so we can see things a little better. Tell you what, I'll just rewrite it down here below. Integral of 1 dx plus the integral of x over x squared plus 1 dx. So over here on the part that's on the right hand side, we'll need to use U-substitution. We'll do u equals x squared plus 1. Du is equal to 2x dx. To make that match the x dx we have, we divide both sides by 2. So we end up with integral of 1 dx plus 1/2 du over u. So now we're ready to take the antiderivative. Antiderivative of 1 is x, then plus 1/2. Integral of du over u is natural log of the absolute value of u plus c. So we get x plus 1/2 natural log of the absolute value of x squared plus 1 plus c. One final note I want to make on this example, what I have written is not in any way incorrect, but I actually don't have to keep that absolute value there. Sorry, plus c. The reason the absolute value sign can go away, sorry my c is not showing up, but there's a plus c there at the end. The reason the absolute value sign can go away is because x squared plus 1 is actually always positive. So there's no need to say the absolute value when it's always positive already. So either answer is technically correct. I'm mainly wanting to alert you to that in case you're ever on a multiple choice question and you see it has no absolute value and you feel like something's wrong. You know, wait a minute, that is okay because x squared plus 1 is always positive. So it's okay in that case if the absolute value sign is dropped. One more example. X cubed minus 3x squared plus 4x minus 9 all over x squared plus 3. Again, what tells us we need to use long division is by looking at the powers. since the greatest exponent on the top, the 3, is bigger than the greatest exponent on the bottom, the 2, or we could say the degree of the numerator is higher than the degree of the denominator, that tells us we need to use long division. So I'll do x squared plus 3 going into x cubed minus 3x squared plus 4x minus 9. And I remember to do the 4 steps: divide, multiply, subtract, bring down. So I first divide x cubed over x squared. So that just cancels out, leaving me 1x. So I've divided. Now I multiply x times both of these two pieces. X times x squared is x cubed, and then x times 3 is 3x. And notice I'm going to write it under the 4x because I want to keep the like terms together. So I divided and multiplied. Now I subtract. X cubed minus x cubed goes away. Then we have negative 3x squared minus nothing, so that's negative 3x squared. 4x minus 3x is 1x, and I'll bring down the minus 9. Now I divide again. Negative 3x squared divided by x squared. So the x squareds just cancel out, leaving negative 3. Then I multiply. Negative 3 times x squared, and negative 3 times 3 is negative 9. The x squareds cancel out because it's negative 3x squared minus negative 3x squared, and so do the 9s. Negative 9 minus the negative 9. So the only thing that stays is x, because we have x minus no x's, so it's just x. So x turns out to be our remainder, and we know our remainder always goes over top of our original denominator. So the original question we had, the fraction inside the integral, is equivalent to x minus 3 plus x over x squared plus 3. I'm going to erase all that and then do the integral with that. So this integral is equal to x minus 3 plus x over x squared plus 3. And I'm not going to bother separately writing them, but just know my U-substitution is only going to apply to this part. U is equal to x squared plus 3. My derivative of that is 2x dx. I do have to divide both sides by 2, or you can think of it as multiplying by 1/2. So I get down to x dx, and I guess I'll go ahead and separate it now. We have 1/2 integral of du over u. So over on the left side, the antiderivative of x is 1/2 x squared. Antiderivative of negative 3 is negative 3x. Over here I'll have 1/2 natural log of the absolute value of u, which is x squared plus 3 plus c. Notice again, we could drop the absolute value there and just make them parentheses, because x squared plus 3 is always positive. But it's not incorrect to leave the absolute value. So make sure you watch your degrees and your exponents, because in a fraction you may at times have to do long division when either the degrees are the same in the numerator and the denominator, or the degree is bigger in the numerator than it is in the denominator.